speak in front of an audience again. This is also very great. So this part of the mini course, well, we'll have a little break now, more or less, compared to what we did earlier. So you will not hear anything about signatures. You will not hear anything about free algebras. In fact, what I want to do is to keep things as basic as possible, to give you an idea of the fundamental basics of reinforcement learning. And the reason why I want to keep it basic is because in my impression, the math finance community has just started to explore reinforcement learning. And I think there's a good reason why it's not taken off yet. Yeah, but hopefully some of you become interested to push this topic a little further into the math finance community or computational finance community. I've split the course up in 3 parts. In the first part, that's first half of today's lecture, we will talk about the mathematical framework, which is Markov decision processes, and then classical techniques to solve these problems. This might be familiar to some of you, especially if you have a background in stochastic control. This will seem very simple because this is just discrete time stochastic control. But I want to have everyone on the same level before we move on to reinforcement learning. And then in the second part of today's talk, we will talk about the fundamental, the most basic reinforcement learning algorithms. And then tomorrow, the first half of the first talk tomorrow, we will talk about more advanced stuff. That's the rough plan. All right, let me start at the very beginning. What are the promises of reinforcement learning? Why should we use reinforcement learning? If you have never heard of it, you may Google it and check the news for reinforcement learning. And to get a rough overview where it is used, why it is used, and what we can do with it. So a big part of reinforcement learning comes from the computer science community. In computer science, this is a well studied subject, and one area where it is big is in robotics. So if you have a robot and you want to train it how to walk, reinforcement learning is one way of doing it. You just let the robot walk, and if it does well, you give it a reward. You encourage it to do more movements like that. And if it doesn't walk, you tell it this was bad, try something else. So you try to reinforce good behavior with the robot. So robotics is one of the big application areas. Self-driving cars is another area where you can use reinforcement learning. Tell the car to go the right way, and not make any accidents. Try to reinforce good behavior in a self-driving car. Especially if you go into the news section, you will probably hear about reinforcement learning, or what Google has done in reinforcement learning. You can teach a reinforcement learning agent to play games like chess or Go. These are these AlphaGo, AlphaZero algorithms developed by DeepMind, which perform much better than humans do. And this is another big area of reinforcement learning. And there's a very good reason why games is really an area where reinforcement learning shines. We will get back to that later. A lot of research is also done in video games, just because you will see in a second why, because the framework fits perfectly to those kind of situations. What else do we have? So we want to do finance. So where can we use reinforcement learning in finance? Let's say trading. So we have a reinforcement learning algorithm or agent do trading for us. And if it does well, we reinforce that behavior. If it doesn't do well, we tell it to do something else. So this is the kind of application that we might be interested in. And I will have a few very basic examples throughout this course on how to do that. Think of optimal investment or hedging. These are the areas where we can use it. Another big area where this is used is recommendation systems. Yeah, so if you go on your favorite shopping website, usually you have some area on there where it recommends products for you. Well, you can train these recommendation systems using reinforcement learning. So it will show you a couple of products, let's say. If you click on them, we will get similar products shown over time in order to maximize revenue for the website. Not just products, but also ads and pretty much anything else. Recommendation systems. Right, so supposedly, this can make our life easier if we have nice systems. And now we want to put this into a mathematical framework. We are mathematicians, so we need mathematics. We need a framework to do this kind of thing. So let's try to figure out what these problems have in common. Underlying is always a dynamic component, something which changes in time. We have some kind of a system. Let's say, let's talk about games. Let's think about a video game. Then each frame, you will be presented with a different picture, let's say, and this changes dynamically in time. And you play this game in order to reach a certain objective, so you have an optimization problem. This may possibly be stochastic, but doesn't have to be. But of course, we are interested in stochastic problems. Another thing where these algorithms shine is if it is very difficult to get the dynamics of the state right. So let's stay with video games. It's hard for you to predict what happens between two frames. So what your action, how the pixels, let's say, change if you do a certain action, or if you have never seen what's coming next, it will be hard to write down the dynamic evolution of frames that you will see. Or in the finance situation, maybe you don't want to write down a financial market model because you don't really believe in it, or you are certain that you will get it wrong anyways. And that's where reinforcement learning is very helpful, usually. On the other hand, so you don't really want to write down a model for the state dynamics, but maybe you have a lot of data available, or you are able to generate a lot of data. Again, video games, you just play. It will show you the next state. You can generate a lot of data with that, but you don't need to know the dynamics, the underlying dynamics. So in other words, well, dynamic stochastic optimization problems, that's for us stochastic control, or if you're in discrete time and computer scientists, you would call that a Markov decision process. Or an economist, they also like to call it Markov decision process. And we are looking for, well, algorithms to solve these problems where we don't really have to rely on on knowing the dynamics, but maybe we can do something which is more data-driven or model-free, or where we don't have to do too many assumptions on the model. So that's the setting where we live in. So let's talk a little bit about Markov decision processes. How do we define them? What do we need? How do we solve them? This is the first part of this lecture. And I brought you a screenshot from my favorite childhood video game. Does anyone know which game that is? Yes, The Legend of Zelda: Ocarina of Time, released '98 on the Nintendo 64. As I said, my favorite game. It was released in November. I know that because it was my biggest wish for Christmas. And my parents had a really tough time finding that game because it was sold out immediately. And my absolute favorite game. Even now, I sometimes play it when I have a little bit of free time. And yeah, we'll use that as an example, right? So we play this kind of game, and we want to win. We want to get to the end of that game. And now in each frame, every time this the video game produces a new picture, this will be our current state. So we can think of, well, each pixel that you see in this picture consists of 3 color values: red, green, blue. And the collection of all of these pixels, from one of these screenshots here, this is our state space. all possible pixel combinations that we have. This might be all possible states that are available. This is what we get in each time step. And now we can do, we can interact with this system by, I have a controller with me, by just pushing buttons. These are the actions that we can do. So this controller here has many, many buttons, and pretty much the power set of all buttons, these are the actions that I can take. So I can press 2 simultaneously, I can try to press 7 simultaneously. And so I have a lot of different actions that I can do. And depending on what I press, I'm presented with a different frame in the next time step. And possibly, so this gives us the state space, these are the pixels, the action space, these are the controls that I have. And I might want to put constraints of the controls that I have. So in this situation here, I don't think there's any constraint at the moment, but in the back, you see vines which you can climb up. And while you are up, you cannot use the shield that you have, or he's carrying a sword over here. You cannot use that while you're climbing. So depending on the state, you may have different actions available to you. So for each state, we have a different set of actions, state constraints. And throughout today's talk, I would say, we restricted a situation where both state space and action space are finite. This is to make my life simple and easier for you to follow. But we can extend this to more general spaces. I will talk a little bit about it in a couple of slides. Okay, and for now, we're not so much concerned with reinforcement learning directly, but we will assume that we have some kind of a transition kernel that you see here, P. So given the current state S and the current action, with the given probability, I'm presented with a new state S prime. So it's determined by this transition kernel. Since everything is finite, I can write it like this. And if I know it, then I can make use of that. Later on, we will try to look for algorithms where there is some kind of transition kernel, but I don't know it. This is the path that we will eventually take. Okay, and now I want to optimize. And the question is, what do I optimize? Well, I need some kind of reward system which tells me this was good, this was bad. And this will be given by a function which depends on current state and current action. So in this situation here, what you see back there, this is an enemy. If it hits me, I might get a negative reward because I'm losing health. Or I might be able to beat it, and then I get a positive reward to encourage good behavior. Or it's actually a bad idea for a reinforcement learning algorithm if you do it like that. The reward should be that you reach the end of the game. You should get a high reward for that. That's what you're aiming for. That's the ultimate goal that you want to reach. And in this setup, it is given. But I think I know what you're hinting at. If you are in a situation where, sometimes you're in a situation where you have to design a reward function yourself, and this can be quite difficult. And depending on how you choose it, life can become quite complicated. So let's say in this video game setting, there is no inherent reward structure. We would have to come up with one ourselves. And as I said, if I get rewards for killing enemies, optimally, I will start running around and kill everything. But I will never reach the end potentially. So I need to write down a reward which encourages what I actually want to achieve. Exactly. All right. So that's the setup. That's all I need for a Markov decision process: finite state space, finite action space, transition kernel, and rewards. I also include a discount factor because early rewards are better than later rewards, to encourage to gather rewards quickly and not take an infinite amount of time. And given these ingredients, I can write down an optimization problem, which today will look something like this. So there's no time component involved, so I play indefinitely, so to say, and I try to maximize expected discounted rewards. And well, what are the ingredients that we see here? The little s here in the expectation, that is the initial state, so what we start with. initial prices of our financial market and initial wealth, or the initial screen on the video game, something like that. Then what you see here, the S pi, this is the state process, so the dynamic evolution of states. The A, this is the process which collects our controls that we do at each point in time. And you see here that they are, well, I have this index pi here. This is what we will refer to as our policy. I will say in a second how exactly these interact with each other. But this is what we can choose. We choose a certain policy, and these will generate state process and control process. A given state and control process, I can write down the discounted rewards, take expectation, and then I maximize over all policies. And I can parameterize everything in terms of the initial state. This is my optimization problem for each initial state available. This is what we call the value function. And the value function plays a crucial role for solving these kind of problems. If you know the value function, you know how much reward you can achieve. And usually, given the value function, there is a way to get to an optimal policy. So what are these policies about? If you're familiar with stochastic control, you would probably identify the policies with this control process. So this would be an adapted stochastic process, which kind of influences or controls the state process. In Markov decision processes, we do that a little bit differently. Here, pi is a function which maps a state to a probability distribution. A probability distribution on the actions that I'm allowed to take. So given a state, I say with which probability I choose a certain action. If I put probability 1 on a certain action, this means that I will definitely choose this one. But I also may flip a coin, and depending on the outcome of the coin, choose a different action. So we have some kind of inherent randomization already in the policy, but it's in feedback form, so I base my decision on the current state only, and not on past states, and so on. And then once I have such a policy, I can just go ahead, start looking at my initial state, choose an action according to this probability distribution. This gives me the first action. This produces a reward and a new state, and then I just iterate this, and this gives me the entire process S and A. Of course, I need the transition kernel to actually simulate that, let's say, or to write down the dynamics. And if you look at it, there are two sources of uncertainty involved here. I have one coming from this transition kernel, so the noise inherent in the system. This might be the noise driving your stock price. And I have noise in my actions. So the one from flipping the coin, which tells me whether I buy or sell. And these are, well, assumed to be independent, which if I write it like this, doesn't make too much sense at the moment. But you will construct the system SA in a way that these noises are independent, or in other words, you want SA to be a Markov chain. That's all. In the language of stochastic control, I would call these randomized Markovian feedback controls. Feedback controls because they only depend on the current state. Randomized because I can choose them randomly, but the randomization does not depend on the underlying system. So I do that in a Markovian way. That's how I would call it. And as I said, this is different to the usual setup in stochastic control, because there we try to avoid the randomness in the control, the additional randomness, because we don't need it. Here for these, as long as we don't talk about reinforcement learning, we will also not need it. You could use deterministic rules all the time. And we usually allow history dependence, even if the underlying system is Markovian. So if you have a Markovian price process, you would still allow, let's say, predictable trading strategies, and then maximize overall predictable trading strategies which depend on the past. But in the optimum, we'll do something which is a feedback form anyway. So here we restrict to that feedback form right away, from the very beginning. Right. Few remarks. we have to talk about, well, whether the optimization problem is well posed. And since I assume that everything is finite, the reward must be bounded. So uniformly bounded in the policy. So as soon as I say that the discount rate is less than 1, the expectation will exist, and the value function will be finite. Another consequence of assuming that everything is finite, we immediately see there's an optimal action, a deterministic one. Let's say I restrict to deterministic actions, then there are only finitely many, because I only have finitely many states, finitely many actions, so there is an optimum. In general, this is, of course, a much more tricky question, but we know there is one. Now it's just a matter of computing it. Randomness in the policy, as I said, is only needed later for reinforcement learning algorithms. So for now, I can just ignore it. Think about choosing a deterministic action associated with each state. When it comes in, when we come to reinforcement learning, then we will ask you more. All right, I've chosen an infinite time horizon problem, but it's not a real difficulty to also include finite time horizon problems in that. You would see an example for a finite time horizon problem embedded into the setting on a couple of slides, or exit time problems. So you stop at a random time when your state reaches, or when you reach certain states, that's when you stop. This is not infinite time horizon, this is not a finite time horizon, but it's a random time horizon, can be embedded in here as well. And the way you would do that is to set all rewards after you're reaching a terminal state equal to 0, and then automatically on a finite time horizon. Yeah, so what about extending it to more general state and action spaces? This is easy, but only easy up to measurability and integrability issues. So if your state or action space is not finite, let's say uncountable in some sense, then everything goes through. The only thing that you have to worry about is measurability and integrability of all objects involved. And I say easily here, but this easily means only given that you have resolved these issues. So this becomes terribly tough on general spaces if you're in a very general setting. But up to technicalities, ideas carry over. And that's the takeaway message. If you want to look at this more deeply, here's my recommended literature. So the first book, Putterman, Markov Decision Processes. This is what I would say computer scientists tell you if you want a mathematics book on Markov decision processes. So it's quite readable, very accessible. It has a lot of results, and it only does the finite Markov decision process setting. So very accessible. Nice starting points. Also a very old book. 2005 is the newest edition. I think it was written. I don't know. I don't want to say, but it's one of the older books. If you want to dig deeper, Bertzika-Shreve is an amazing book. They go beyond that finite setting, and there you will see all the issues, the measurability and integrability issues arising. That's the book. So 96 is the newest version. It was written in 78, I think. So that's from that we learned it's a well-established theory. Markov decision processes. If you want to look at applications to finance, Boyle-Rida is a nice book, also very accessible, and they try to convey a lot of intuition, and it has these applications to finance if you're interested in that. And if you don't care too much about mathematics and only want to learn about reinforcement learning, then Sutton-Barto is a great introductory book to look at. The second one, so Bertzika-Shreve and the Sutton-Barto book, they are available for free online. So good starting points. Let's go ahead with an example in finance, optimal investment. So I start with a nice financial market model, discrete time, de-risky assets, could be any model you like. And then I have to think about what my state space is. So eventually I want to optimize my utility of wealth at some fixed point in the future. let's say at my retirement date. So I need to keep track of how much time is left. Yeah, so part of my state space will be time from 0 to capital T. I should keep track of my wealth, yeah, which we will assume to be something strictly positive, and because I don't want to go bankrupt. And I also keep track of the prices. Yeah, these are also strictly positive, and I have D of them. Yeah, so that's my state space. What are my actions? Well, my actions are how many shares of these securities I hold at each point in time. So this can be any RD vector. Straightforward. And once I have that, I can write down what my wealth looks like, evolution of wealth. And it's very simple. My wealth at time n+1 is my wealth, the time instant before, plus profits and losses from trading. Increment of the price multiplied by, well, how many shares I hold. Here, this is my policy. You see it, pi I. And I plug in, well, the state. And the state is current time, current wealth, price. Yeah, so these are the decision variables I have at hand, on which I can base my decision. And this will, of course, give rise to your transition kernel, which I don't write down here. I want to enforce a couple of state constraints because I don't want to go bankrupt. I'm not writing them down, but I'm just writing, I only look at policies for which my wealth is always positive. And then I want to maximize utility of wealth at my retirement date. And so I'm optimizing expected utility of wealth at time capital T. And if I want to embed that into this reward structure, this just means that, well, my reward is given by utility of X, but only if current time is capital T. Yeah. All other rewards are set to 0, and then everything just drops out. There's no discounting. I set beta equal to 1, and then I'm in this setting. We will come back to this example a couple of times. For now, this is just the model. How do we solve this now? So there are a couple of ways. Again, if you know stochastic control, then this might be straightforward for you, but I want to have everyone on the same basic level at least. There are two main approaches. One is dynamic programming, which you will see here. The other one is maximum principle, which we will not cover because reinforcement learning is based on dynamic programming. And the big idea behind dynamic programming is that decisions and optimal decisions are time consistent in the following sense. You can write it like this. On the left-hand side, you have the value function with initial state S. This is the best expected total reward that you can attain from time 0 all the way to the end. And here on the right-hand side, it says that it is the same as collecting all rewards up to time n, or before time n, so n-1, okay, 0 to n-1. And then at time n, from that state we are in, act optimally. So this is splitting up your time period into 2 sub-periods. You assume you know how to act optimally from time n onwards. Then everything you have to do is just optimize the state at time n. And that's the same as optimizing from the very beginning all the way to the end. In that sense, it's time consistent. If I recalculate my optimal action at time n in that state, and I paste that to the optimal action I've done up to that point, it's optimal all the way on the entire time interval. That's dynamic programming. And in this situation with these finite state spaces, given you have an optimal policy, extremely simple to verify. I don't go into the proof, but I think the intuition is enough and the intuition is hopefully okay. We will use it mostly in the case n = 1. So we make one action and then act optimally afterwards. So it rewrites like this. We receive the immediate reward for choosing our action A. And then we discount the value function afterwards. So we only care about our action today and then worry about the optimal action afterwards tomorrow. One way to think of it. And since everything is finite, I can actually write that down more appropriately. So instead of maximizing over all policies, I just maximize over all actions which are allowed. Ignore here that we are able to choose probability distributions. You can show that it boils down to choosing a deterministic action, mainly because you only have a deterministic state available anyways. You know your initial state, then you choose an action, receive that reward. And then since you know the transition kernel, you can compute the expectation here. So you're just weighing your value function in the new state S prime with the probability of getting there given your current state in action. So that's a very important equation for us. And of course, you maximize, you choose the best action to optimize the records. So as I said, this is kind of, I think of it as time consistency. This is often called dynamic programming principle. The computer scientists and economists call it Bellman equation or Bellman optimality principle. There are many ways of phrasing this thing. I call it dynamic programming principle. Okay, and as I said, easy to prove. If we are in a situation where we have an optimal policy, terribly complicated to prove, if not. If you're in a very general setting, if your state space doesn't carry much structure, these proofs are extremely hard. Same for continuous time, very, very hard proofs. But we don't care about it because I will only use it as a heuristic, as an idea to get towards an optimal policy. And because just by looking at it, it is somehow clear what to do. Suppose I know the value function, then my optimal action in state S is just the maximizer of this. And that's actually great, because we can turn this dynamic programming principle around in the following way. Suppose we have a function which satisfies the principle. So we take a function W, which satisfies the dynamic programming principle. It's the same thing, just value function replaced by W. And since we are maximizing over a finite set, we will be able to find optimal A's. And this will then be our policy. We just choose something from the argmax over here. And then you can show if you have such a pair, the W must have been your value function and pi star is optimal. That's what we call a verification theorem. You verify that if you have a solution of the dynamic programming principle, this must have been your value function. And since this is important, I have a proof for you. So you start with an arbitrary policy, and you write down this function W at time S, or in state S. Sorry. Pi A given S is the probability of choosing action A given that we are in state S under our policy pi. There's a probability distribution, so it sums up to 1. So I've multiplied everything by 1. Now W satisfies the dynamic programming principle, so I can estimate W by this expression here. This is the right-hand side of the DPP with a particular choice of policy. So DPP was with a max in front. Now I just choose that action which I have chosen according to the probability distribution. So get a greater or equal. And now I just compute that. So this is really just an expectation, right? So we're multiplying probabilities here and here by certain objects. And if you do that, that's the reward in our initial state with that action A under our policy. And then beta times, well, what we have here is W evaluated at the state that we moved toward. And then here again, I have this W, which in the same way as above, I can estimate by some expectation. So I do it again. Greater or equal, I receive the next reward, and I am at step number 2. I have to employ here a conditional expectation, but since everything is Markov, I can just pull it out. and ignore it. Yeah, so I receive the first 2 rewards and then get the discounted W at stage 2. And now I continue. I do it n times, so I receive n rewards and have beta to the power n W, and then pass to infinity. That's something I can do because everything is bounded. And beta was assumed to be less than 1 in the theorem. So the last term just vanishes. And I end up with this. Expected total reward under the policy pi. And pi was arbitrary. So I can take the supremum here over all policies. And then I see that W must be greater or equal to the value function. And now if I choose my candidate for the optimal policy, then instead of an inequality here, I get equality, because pi star assumes the maximum. So I get equality everywhere, meaning that W is equal to the expected total reward under pi star, but greater or equal all other policies. So it's the best. Pi star must be optimal. But if it's optimal, then the expected total reward under pi star is the value function, which we have just argued to be equal to W. So value function and W must be the same. So it's just repeatedly plugging in the dynamic programming principle once you have found a solution of that. Very simple proof. And that's it. Now let's try to use that to solve the optimal investment problem. And in that situation, life is even easier. So what we want to do now is we want to solve the dynamic programming principle in that situation. And the nice thing is that we have a time component. So we know that if we are already at, I should have written capital T here, if we are at terminal time, actions don't matter. So because we only receive utility of our current wealth, and that's it. No more actions available because time's up. So we already know our W at time, capital T, should be equal to this utility function. And then we write down the dynamic programming principle at any point in time earlier, one step, and tells us supremum over all actions. Here I write supremum because these are uncountably many. It's not a finite problem. But I can assume that at time n, I have wealth x and prices are p. I won't receive any reward because I'm before time capital T. And the next state is, well, next time instant, next level of wealth, which is current wealth plus profits and losses from trading, and then the next price. And from that, you see, you can solve this problem iteratively backwards in time. I start at capital N, set my function equal to the utility function, and then I compute it at capital N minus 1 using this expression here, because I can just plug in utility of wealth in here, use that to compute W at time capital N minus 1, and then work my way backward. And that's what it says here. Just optimize and then compute W. And if you do that here, I've done it for the simplest possible scenario. So we use a binomial model where we only have one risky asset, which either goes up by a factor of u with probability q, or it goes down with probability 1 minus q. And my utility function is log. And then if you go through the calculations, you will see that W is actually logarithm of x plus something which only depends on time. And your optimal pi star at time n with wealth x and price p multiplied by p over x is a constant, which you see over here. This has a very nice interpretation, because what you see on the left-hand side, this is, so pi star is the number of shares that we hold. If we multiply that by the price, that's the wealth we have invested in our risky asset. And if we divide that by our current wealth, that's the fraction of wealth we have invested in the risky asset. And that is kept constant. The constant fraction of our wealth we invest in the risky asset. and then it's solved. We will see a plot in a second. Now, this is a very boring example because it's so simple. But let's suppose we want to do something which is maybe less tractable. And one constraint that I like to enforce is we assume that assets or securities are indivisible, meaning that you can only buy, or the number of shares has to be a natural number. You cannot buy half a stock. You can only buy natural numbers. No short selling, no borrowing of money. So you have to invest between 0 number of shares and your wealth invested in the risky asset cannot exceed your total wealth. And it has to be a natural number. From a mathematical point of view, this is a bad constraint because it's non-convex. So if you're in a continuous time setting, this would be terrible. Here the situation is nice because this enforces that the number of actions that you have in each state is finite. Because your wealth is finite, lower bound is finite, and the number of shares in between must be a finite number because it must be a natural number. So given your initial wealth, small x, let's say 100 euro, we start with 100 euro, and then you only have finitely many actions that you can take. Since the price only takes 2 different values, in the next step, there's also only finitely many states available. So in each point in time, finitely many states, finitely many actions. Then we are really in this finite Markov decision process setting, and I can solve the dynamic programming equation numerically. And if I do that, I get a picture like this. So how do we read this? Down here is our total wealth, so X, and up here is our wealth in the risky asset, pi times P. The red dots that you see here, these are all the possible states that I can reach. The black line that you see here, this is the optimal fraction that we have if we don't enforce constraints. So we keep the proportion of wealth in risky asset and total wealth at a constant level. This gives you this line. And if now, in addition, you enforce this trading constraint, our intuition would tell us that, well, we cannot perfectly get to that fraction because it might tell us to buy half a share. Then we just try to go as close as possible. So either by 0 or 1. And the green dots that you see here, these are the optimal positions that you end up with in all possible states of the world. And you see they are somehow clustering around the optimal action without constraints. It diverges a little bit down here for low levels of wealth. Not quite sure why that is, but I think it's still reasonable because what this picture is lacking is what the prices are. So these might actually be the closest points to this black line. This cannot be seen. But that's the intuition, and it's more or less confirmed by solving this. And this is an exact solution because finitely many states, I can compute everything perfectly. All right. That's more or less it for Markov decision processes and dynamic programming. So the first part of the first lecture that I want to give. I want to conclude with a couple of final remarks. So first of all, these finite horizon problems, they are pretty nice because we just saw we can solve them by backwards induction and finite state space. So there's a well-defined numerical way of doing this. But this needs that everything is finite, otherwise it becomes more complicated. What do we do if we really have an infinite horizon problem? Then, well, the dynamic programming principle is a fixed point problem. And even that is still nice in a certain sense, because the operator which maps W to the right-hand side of the DPP can be shown to be a contraction if you discount, if you really do discounting. So in other words, Banach's fixed point theorem will tell you that if you do this kind of iteration, you start with a W0, compute the right-hand side, this gives you a W1, and you continue like this. This will converge to a solution to a fixed point of that operator. And then you have your value function. And once you have your value function, you can compute the policy. It is expected that this is a little bit harder if you're an infinite time horizon, and because infinite time horizon problems are just harder. You don't have this backward induction available. Same as in continuous. Yeah, but this also gives you, in principle, a way to approach these kind of things. Yeah, and then we are pretty much done. Yeah, we have solved Markov decision processes, these finite ones. We don't have to care about reinforcement learning or creating an artificial intelligence, which solves these things and maybe solves more than we actually want to. So that's pretty much it. Sorry? Exactly. That's why you have to be very careful with the reward terms. So now I can solve my favorite childhood game, right? I just write down everything that I need to know, solve the dynamic programming principle, and be done. But of course, that's not the case, because it's just not feasible. Because if you actually do that, computations become quite costly. If either your state or your action space is large. Here the state space is, well, number of pixels in your frame by 3, because each pixel had 3 color values. And I don't know what the resolution here is, but you can imagine the state space is quite large. And actions are also quite a number. As I said, I don't know how many buttons are on here, but at least 10, 11 different actions that you can take. And you have to choose the power set of that. So 2 to the 11 actions that you can take at each state, so to say. This becomes large very quickly, and then computations become inefficient. And of course, here, I would never be able to write down the correct transition kernel. Because I don't know how this game was programmed. So I still can't do it. I need more. And that's what we will do in the second part, which is about to start right away. Maybe do you have any questions at this point? Okay. Then one quick intermission. Let me show you how fast this goes. So here I programmed the optimal investment problem with dynamic programming. 3 time periods, I think. That's how quick it goes. So that's actually quite efficient. That's the same picture that you saw on the slides. Here's a little bit larger. You see that here it kind of seems to diverge from that line. As I said, I don't exactly know why that is, but that's what comes out. And let's stop this. Down here you can see, well, what we need to know. So value function, it tells us at initial time with wealth of 100 and the initial price of 8 is 4.7. This doesn't tell us anything. The optimal action in that state is 6. So we buy 6 shares. Number of states that we have available is 482. So that's all combinations of time, wealth, and prices. And that's only 3 periods. So that's already quite big. A number of state action pairs. So if I, in addition, include all possible actions, I already have 2,551. These are all possible states. And that's only 3 periods. And if I increase the periods, of course, this becomes much bigger, much faster. So this will eventually become very inefficient. Okay. Now, what do we do against this inefficiency? We'd use reinforcement learning, maybe. So, a couple of preliminaries. Let me repeat one more time. This is our Markov decision process. This is the problem that we would like to solve. And we just saw dynamic programming is a way of approaching this. So this is once again the dynamic programming principle for one step. Immediate reward, and then we don't care about the next state, we care about that tomorrow. And as I just mentioned, this will become quite costly if we have a lot of states. We may not know the true transition kernel. Just a reminder of what I just said. And now we suppose that maybe we are able to simulate from that state process without knowing the probability distribution. So in the game, we just play it. It will present us with samples. We record them. Or we look at the market and look at the prices. So if we can simulate, we may have a lot of data available. That's the other option. Either a lot of data, or even better, we can simulate to produce an arbitrary amount of data. What can we do then? So that's the big question now of this second part. And I want to start with a little bit of notation. We already know the value function. And for what we will now have to do is we need a way to evaluate how well a given policy performs. So we need to compute somehow the expected total reward under a given fixed policy pi. This is what we call the value function of pi, small index pi. And also what we know from the dynamic programming principle, we mostly care about what action do we take in which state. So maybe we might be interested in what is the expected total reward that I can get if I'm in state S, and I already know that I will use action A. This is called the Q function of pi, because it's denoted by Q, or action value function sometimes. So you are conditioning on starting in state S and using as first action A. And afterwards, you follow your policy pi. Then you try to evaluate, well, how good was it to choose A instead of whatever pi told me to do. And if you optimize over all policies on the right-hand side, this is the so-called Q function. This is the optimization problem where we fix the initial state and the initial action. This is a great thing because dynamic programming told us that, well, that's all that I need to do. If I know Q, I only have to optimize over A to tell me what the best action is. That's why we need these Q functions. And of course, they are related. Here are a couple of relations. Value function of pi, if I maximize over all policies, that's just the value function. That's obvious. Same for the Q functions. If I have the Q function of pi and I optimize over all pi, by definition, this is the optimal Q function. If I want to know the value function, I just look at the optimal Q function and maximize over A, because Q chooses the optimal policy, and now I just optimize also the first action that I do. That's the best I can do. Or value function of pi. This is here, the pi is fixed. So we have a distribution of actions. So once I know which action I take with a certain probability, I can evaluate that using the Q function for pi and plugging in whichever action I take. So it's the expectation of Q pi. So conclusions. Well, if I know Q, I don't need to compute V, because it has more information available, because from Q, I can immediately get the optimal action. And that's something which is done in Markov decision processes, which you don't see in continuous time stochastic control. You work with these Q functions because from them, it's much easier to get an optimal action. In continuous time, you can't do that because your immediate action has no effect in continuous. And so now instead of computing the value function, I compute the Q function, more or less. And I can do that by optimizing over all these Q pi's. So if I have an algorithm now, I start with a given policy, and then I need to evaluate how good that is. So I need to compute Q pi. So I need an efficient way of calculating that expectation. That's the prediction problem. For given policy pi, compute V pi or Q pi. And if I've computed that, I can check or try to figure out a way of how to choose an optimal action. So how do I improve my policies? Find an optimal policy. That's the control problem. And these are the two things that we are now going to look at. How do I get an efficient estimate, or any estimate, doesn't have to be efficient. And once I know how to compute these things, how do I improve on my policy? And we start with prediction. Let's do it naively. It's an expectation. Let's do Monte Carlo. We can simulate the state process. That's our assumption, or we have a lot of data available. So let's suppose we can compute this infinite sum here. Somehow we'll get rid of that in a second. So this is a realization of a random variable, realization of the total discounted reward. And then we do Monte Carlo. We just average over all the total rewards that we have observed. This should be, if the law of large numbers holds, which it does, since everything is bounded here, this is an approximation of v pi. All this small v pi with an m over here. And if we are simulating, we can produce more and more data. So it might be a good idea to do that iteratively. So I've computed my estimate with m Monte Carlo samples, and now I get a new realization of the total reward. So what's my estimate with m plus 1 samples? So definition would be that, but I would be stupid to compute this entire thing because I already have the previous estimate, and you can guess immediately that there's a way to use the previous estimate. You just get the last realization of the total reward outside of the sum. You see it here. You have to put a 1 over m plus 1 in front. And then what's left is the sum up to capital M, which gives you up to a rescaling by m the previous estimate. That is the obvious and trivial rewriting of the equation. And now I rewrite this even further because I realize that this fraction here, capital M over capital M plus 1, is 1 minus 1 over M plus 1. So I split the v pi up into 1 here and a minus 1 over here. And I have to multiply by this 1 over M plus 1, which are now called alpha. So this has a very particular structure. That's why I do this rewriting, because all the rules that we will get to know will have this structure here. This motivates what we're doing next. And since this has become unreadable because there are so many indices, I will now write this more compactly like this by dropping everything which pertains to M. So I get that my new estimate is the old estimate plus this alpha times the realization of the total reward minus my old estimate. Sometimes also read as new estimate is old estimate plus learning rate multiplied by target minus old estimate. That's what the computer scientists would call this equation.
It also relates to this sort of gain when you add more information and you have like, the second term is the innovation, right?
Yeah, exactly.
You can see it from the conditional statistics too.
Right. You may call this the error that you made in your previous estimate.
Exactly.
Somehow. And you're moving towards the target using that learning rate. So we rewrote this just to get to this this kind of form, because I think this is quite natural to understand. Okay, so summing up, if we want to do naive Monte Carlo, then this expectation is computed iteratively by this update rule. Now the only question is how do I compute this infinite sum? I won't be able to do that. And the main idea, and this is, I think, the only thing that you have to understand these classical reinforcement learning algorithms. We do have other representations of v pi. For example, we have some kind of a dynamic programming principle also for the v pi. You can think of, well, what's the total expected reward that I get for fixed policy pi? well, I get this reward, and then I discount whatever I get in the next state. And this is also time consistent. And now up here in the first line, this is the expectation we wanted to approximate, and we use this rule. Now we have this expectation. What's the rule that we get? Well, we use the realization, or we try to get a realization of what is inside the expectation, and use that as our new target. So reward, immediate reward, plus beta times whatever we get in the next step. We don't have that particular value yet, but we can use our estimate we have for that state. And that's what we call temporal difference prediction. One step, because I use dynamic programming for one step. There's also n step, where you receive n rewards and then discount by beta to the power of n the other estimate. And this is the basic prediction rule that we use in reinforcement learning. Now, of course, you make an error with that, because you're using in your target, the way you want to, the direction you want to go to, something which you have predicted earlier, which is wrong. So there's a bias in there. But nevertheless, this can certainly easier be computed than what we have up here. That's prediction.
No, turn around.
It's actually just a short question. This S1 depends on S, right, in some sense, and small s.
Yes, so S1 is what you get when you start in small s and use the policy pi.
Okay.
So you're simulating a path, let's say, and then let's go to the next slide. That's actually a good thing. So you're simulating the entire path, S, using a policy. And then when you are in state Sn, you update your estimate using reward in that state and the next value in the next state. So like that with one path, in this infinite horizon problem, you keep updating all the states as you go along. Because we don't just want to compute v pi in a given state, we want the entire function. So we have to go through all points anyway. So why not use the path that we simulate? And if you want to go away from, so as I said, we actually want these Q functions because they are more useful. But you can do the same thing. Old estimate is, well, here you need to write down the dynamic programming principle for QPy. What does that? You still get the immediate reward, because your action that you're using is fixed. And then since you've sampled the entire path, you know that in the next time step, you will be in Sn+1, and you already know your action. So you can use that as an estimate. And this is what is really used, not the V version, but the Q version. And this is what we call SARSA. Why is it called SARSA? Because it says so. We need current state, current action, reward, next state, next action, SARSA.
So in terms of interpretation, when we try to more or less think about this and compare with dynamic programming, right? What we are avoiding here is to compute the expectations, essentially. So this will be like a sort of a stochastic gradient descent, policy iteration towards avoiding the computation of all those expectations. Is the right way to get some intuition on this?
Yeah, so that's exactly what is happening. So in this simple situation, we do Monte Carlo. That's just the first approach to these kind of things. But you can imagine if you're in a larger state space, maybe you want to do something else because you have to visit so many states, right? So you could just approximate your function by something else, or your expectation by something else, to some kind of regression, where things are moving after these initial ideas. So what we will do, what we will talk about tomorrow is, well, what if we try to approximate our functions here by classes of parameterized functions, and then we do something more in that direction. And if you want to talk about convergence, what you need is stochastic approximation theories. And we will see that actually in a second.
Just to follow up on this, I mean, the way it is written, if I understand it correctly, is based on paths, right? I mean, you start first by giving some Q value or V value defined everywhere. And then as you start throwing paths, different values will be updated along the paths.
Exactly.
The others will be untouched. So it is possible that by doing the osmotical simulation, you will cover some kind of cone that will be updated and the rest will be untouched, and it will not matter because it's not relevant in terms of the paths. Or
it's a great comment, because that's what I'm aiming at next.
okay.
Since you're going along this path, and this is Monte Carlo, if you want convergence, you need to ensure that every state and every action will be visited arbitrarily often. Otherwise, the estimate cannot converge. And we need the entire function. So we have to visit everything. And this is the so-called exploration requirement. Some call it the exploration problem. I think requirement is a bit more optimistic. But it tells you, I think from where we derive this, it is clear why we need this, because it's Monte Carlo. And if you only have finitely many estimates, or if you have states or actions which you never explore, your estimate is wrong. And then dynamic programming cannot work. And
So again, just to follow up on this, in terms of the randomization that you would need to actually do that, right? You're trying to define a function everywhere. So if you begin with time 0 to time t capital, the first thing one has to do is to randomize the initial condition, right? Okay, and then hopefully that will cover. If not, you need to actually add extra randomization without screwing up the dynamics.
Exactly. Yeah, exactly. Yeah, great point. Okay, well, let's suppose that we can somehow achieve this, or we now have a way of estimating Q functions, let's say. And next question is, how do we control? We can now evaluate policies. How do we make them better? Given our algorithm, how can we tell it this was good, this was bad, you should do that? Here, policy improvement comes into play. And the starting point here is, let's suppose we have two policies. A policy pi, where we have already computed the value function and the associated Q function. And now suppose that in that Q function, I choose next the action according to our second policy, pi dash, in that particular state. And this somehow makes it that Q is bigger than V in all possible states. So intuitively, this tells us the action that pi dash or pi prime here chooses is better than what pi wants to do. And you can prove that this is really correct. Pi prime will then be better than pi. And here's the proof. It's very simple. I start with that inequality. And now the right-hand side, I can write this using, again, one of these dynamic programming equalities. So what is it? Here I start in state S, and then my first action must be pi prime. So I receive the reward when I use policy pi prime. Then at time 1, I'm in S1, but computed using pi prime. And then I have to follow policy pi. And that's the value function of pi. But now I have, once again, a value function of pi, which I can estimate by q pi. So I plug that in, greater or equal. And now you see where this is going. I once again use the dynamic program equation for q pi, and then I accumulate all the rewards and just iterate it through. And eventually I will reach the total reward. And now here, the entire state is computed according to pi prime. So that's the expected reward under pi prime, or value function of pi prime. So we've concluded that pi prime is better. Just by iteratively doing that, but we have to ensure that really in each state pi prime is better than pi. And now we just turn that around. Yeah. So how do we improve a given policy pi? Well, we just maximize over the actions in the Q function. And then it will certainly, so that's the best that we can do. Okay, and now you do that iteratively. You start with a given policy, pi 0, and then you compute Q pi 0, maximize in each state over all the possible actions, call that pi 1. And you iterate that through, and the hope is that we will improve in every step, and by the argument on the slide before, we will really improve. Yeah, so what we will see is that the values start increasing. Now the big question is, do they increase to an optimum? I don't know, but the answer is yes. Yeah, and here once again the finiteness of the state space helps, because you have only finitely many states, finitely many actions, so you can only improve finitely many times. So eventually you will not be able to improve your value function anymore. Once they are the same, then, well, they are the same, but pi k plus 1 is chosen in exactly a way to maximize this expression with the value function of pi k over there. That's the way that we chose these maximizers, according to this. So then you have v pi k is equal to this expression on the right, which we recognize as the dynamic programming principle. So once the values stop improving, the dynamic programming principle is satisfied. And when we have the verification theorem telling us, oh, this must have been a value function, and the action is optimal, we're done. So that's the second component, the control problem. Start with an arbitrary strategy and keep improving it by using this one. Yeah?
You said something like you have finitely many states and actions, then you will get finitely many steps. Is that so, or I misunderstood?
That's really the case here. Yeah.
And why do you see that it will be only finitely many steps?
States. States.
States,
steps.
but not steps, right?
So you have finitely many states and finitely many actions, so you can only improve finitely many times. So it's really true in this context that after finitely many steps, you stop improving.
Okay.
Yeah, that can be argued for. This is one of the basic results that you need. But you need finite number of states and finite number of actions.
And still, those may become very large if the dimension of the state and the actions are
exactly
large, right?
Yeah, so you can, an upper bound is probably the number of states by number of actions, something like that. That's the number of iterations that I think, more or less. Not 100% sure, but you get an upper bound, but this grows very fast with number of states and number of actions. Yeah, so while in theory, this is nice, in practice, this is a different story. And of course, this assumes that I know these Q functions perfectly. Yeah?
Okay. That's why it was.
All right. So now we have prediction, we have control, we just have to put everything together. So what do? Start with a policy, predict the Q function, improve the policy, compute the next Q function, and so forth. Yeah, it's just a matter of switching back and forth between prediction and control. And we are done, right? No, yeah, because we work with estimates, so it's a little bit more intricate. And now, what is the big problem? It's the exploration thing again. So policy improvement tells us that I always choose the best action. Prediction, we saw that we need to visit every state and every action. If I always choose the best action, I cannot guarantee that I visit all actions. Yeah, this will not happen. So that's a bad idea. Yeah, to do that, this will not converge typically. This is called choosing the greedy action, which I think is kind of nice. Yeah, if you're too greedy, if you always choose the good one, then it will not converge. So what do we have to do? We somehow have to ensure that, well, we still keep exploring everything. And this is where the notion of epsilon greedy actions comes into play. So what you do is, with a small probability epsilon, you choose a random action. You don't optimize, you just choose something. Yeah, positive probability on the entire set of actions that you have available. So you keep exploring all actions, and with this, hopefully all states. And with probability 1 minus action, 1 minus epsilon, you do the greedy action, the optimal one. This improves estimation, but of course you won't get an optimal action because you always choose something random. So you will have to make sure that epsilon somehow converges to 0 as you keep running that algorithm. And now with that, we have all the ingredients that we need for our first reinforcement learning algorithm, SARSA, called on-policy temporal difference control. How does it work? We will see that in a second. It depends on the situation. Let me just open it up. So initialize your Q function arbitrarily, your estimate. And if you're on a finite time horizon, you simulate path from 0 up to terminal time, and then you're done and you have to sample a new one. And here you have to randomize the initial conditions so that you get all initial states visited at every point in time. This is what Raoul just said. If you are on an infinite time horizon, in principle, you just could simulate an arbitrarily long path. If that keeps visiting everything, that would be okay in principle. Given your initial state, you choose your initial action. You use these epsilon greedy things according to your current estimate Q of the Q function in that state. And then you step through the Markov decision process. So you take that action, observe reward, and the next state. This gives you the next action. You have to sample that. Again, do it in an epsilon greedy way. And then you have S, A, R, S, A. So you have SARSA, you can update your Q. You just simulate one step at a time. And you switch between updating your Q function and updating your policy in that particular state. You're switching back and forth state-wise along the path. That's SARSA, one of the most basic reinforcement learning algorithms that we have. What about convergence of this thing? You really have to think about this because the estimate is wrong and you're doing it along a path and you have to ensure somehow that everything is visited, and this epsilon has to be sent to 0, and you have to choose this learning rates, but you can't ensure that this actually works. So there are convergence proofs for SARSA. You have to make sure that the learning rates, so these weights we get from Monte Carlo, really look like Monte Carlo. So they diverge if you sum them up, but they converge if you sum up the squares. So 1 over m summed up is infinity, 1 over m squared summed up is finite. Be careful here, my notation is bad. For each state that we have a different learning rate. So this is actually alpha n of s, possibly also a in that situation. So in each state, you need a particular learning rate, because each state has its own Monte Carlo estimate. So you need to adjust that depending on your current state.
What would make it change? I mean,
you
will be scaling essentially the sequence 1 over n, just to give an example, but what would be the constant that comes with that? That is what depends on S and A, right?
Yeah. So yes. So we would see an example in just a second how we do that. My advice, so what worked well for me in the examples that I have implemented is really just counting how often I've visited a state, and then do 1 over number of visits, and this works reasonably well. We will see that running in a couple of seconds. So what I really don't like is this epsilon greedy business. This is not this is somehow annoying, yeah, that we still have this randomization, although we want to get to an optimal control. How do I choose this epsilon going to 0? How fast do I do that? If I do it too fast, I won't explore enough. If I do it too slow, I will never get to an optimal action. Yeah, so there's a funny business going on there. And I don't actually know of any good way of choosing epsilon, but we don't really need to, because there's another idea which will lead us to the second algorithm, which is the following. Suppose we don't just have one policy, but two, and they're in charge of different things. So we have one policy, the behavioral policy, which we use for generating the path. This should be one which explores. But we don't choose our optimal action from that policy, but we actually have a second policy, which we will use to, well, update our Q function, because the small q from the slide before, we want this to converge to the optimal Q function. So we have to choose somehow the optimal action in that, in our computation of Q. So we can do that maybe with a different policy, yeah, to get a better approximation of Q and a better approximation of optimal. This can be done, yeah, and this leads you to what we call Q learning. This is off policy temporal difference. It works exactly the same way, only the update of the Q function is different. Yeah, on the previous slide, here we chose a particular A, namely the one from the policy generating the path. Now we just choose the optimum. Yeah, so that's our control policy, yeah, which we use as an estimate, as a better estimate for Q. And then the policy that we use for generating the path, we just have to ensure that it keeps exploring. Yeah, so we can do epsilon greedy, but keep epsilon fixed. So it will always keep exploring, and we don't have to touch the epsilon. Not necessarily, we can, and it sometimes improves things, but yeah, so exploration is easier to ensure. And for our estimate of Q, we just always choose the optimal. This is Q learning, called off policy, because we are updating off the policy. We use a different policy for path and for updating.
So just to rephrase to see if I understand, the pi-b policy ensures that you visit everywhere, and it's a fake dynamics essentially that enforce a path that will cover everything eventually. And the pi is the policy you seek, and you still sort of try to follow the dynamic programming principle to update it, not caring that actually you will jump not to the best state, but the one that the other is enforcing.
Yeah. So the idea, pretty much, you can see from here. Q should be the optimal Q. Yeah? So we will already have the optimal policy. And in Sarsa, what we do is, well, we update it using our current value, the next reward that we receive, and our current guess for the Q. Yeah? And we hope that the policy that we are currently choosing is already optimal. Yeah, so we plug in that particular action A. Whereas in Q learning, yeah, we try to improve things and choose possibly a different action, maybe the best one. So in that sense, this might be a better estimate for the Q function, because it optimizes over the next action.
So it is closer to what you would do in the dynamic programming.
Yeah. So Sarsa is dynamic programming for Q pi. Q learning is dynamic programming for Q, in a sense. Yeah.
Thank you.
Okay. Yeah. So also Q learning can be shown to converge, which is great under the same conditions. So on the learning. Now we have a couple of minutes left. So I want to show you numerical examples. And I do that once again in this indivisible asset setting. Here is the results that we had for dynamic programming. And let's see. let me run this. It takes a bit of time. While it is running, I will explain what is going on. So, oh, that's too far. Yeah. So that's dynamic programming. And here is what I get if I do Q-learning. Now let's go back and forth. You see that not so far off. It gets the tendency right. Yeah, it's not perfect, but it's an iterative method. So yeah, if I keep letting it run, it would probably get better. Yeah, hopefully. And it's really not too bad. And you would see in a couple of, I hope, just seconds and not too many minutes, the results from the algorithm running live in the background. Just by looking at that, let me draw a couple of observations first. So you saw how fast dynamic programming was. Yeah, it's just a split second, and then it was there. Q-learning is still running. Yeah, it takes longer, but that's to be expected, because it has to evaluate the entire state space and action space many, many times. Yeah, run through it to get better updates. Q-learning requires a lot of data. So the picture that you will see in a second from the algorithm, this takes, I think, 500,000 paths. You will see that this is not enough. All right, so the picture that you see here, so this result is by using 1 billion paths. All right, so we need a lot of data. There's a reason to that, because that's really the crude Q-learning algorithms. There are ways to improve this. Yeah. This is just the most basic version. Yeah. We just throw them away right away. Yeah. And we only need the increments actually. Yeah, because we are only updating the current state using the next state, and then everything else can be thrown away. Yeah, so it's memory efficient. Yeah, up to you have to store everything for every state and every action, but yeah, the data generation is definitely okay. Yeah, both algorithms run into troubles when states and actions become large. Yeah, this we will talk about tomorrow for a little bit. I think in both cases it is kind of obvious, right? Why that happens, especially for Q-learning, because you have to explore even more states and even more actions. You need more data, and yeah, this is well. And as I said, yeah, this is really just the most basic version. Yeah, there are ways to improve these things, and yeah, we may have a chance to talk a little bit about this tomorrow. One observation that I made when I tried to implement this, this is a really basic example, right? This optimal investment problem. It's pretty much as simple as it gets. You have to be still very, very careful with the choice of learning rate. Yeah, if you choose the wrong learning rate, this will not converge. Yeah, this is, I mean, kind of obvious, yeah, because we have this convergence result for specific choices of alpha, but these are theoretical results. Yeah, we will never pass to infinity anyways. So in implementation, this is sometimes a little bit different. But what works, yeah, in that particular example, which is running right now, is you choose alpha as 1 over the number of times that you have visited a certain state. Ah, there it is. That was, I think, 500,000 samples. We'll check it in a second. And you see this is not as good as the one that we saw in the picture before, right? Still has a tendency in the right direction, but it is certainly not that.
So if I understand correctly, if your state space is such that dynamic programming runs, you wouldn't use this other thing.
Say it again.
If your state space is sufficiently small, I mean, such that you can run the dynamic programming algorithm, you wouldn't care for this other thing. You only care if the other option is not available, or am I missing?
The point is somehow a little bit different. You use dynamic programming if you have the transition kernel, because you need that.
Yes.
If you don't have it, then you have to rely on something like that. Yeah, that's more the motivation of why you would do that.
Okay. So
and the idea is simple in a way. if you have more information about your model, you should use it because that makes it faster. If you have the transition kernel, you should use it.
No, I didn't check. I mean, I didn't get this this difference, right? That in one case you were making the assumption that you knew the transition kernel, and the other you didn't.
Exactly. So Q-learning is really just throwing the data at the problem. You're evaluating along the path. Of course, I'm simulating the data using my transition kernel. But in principle, if I have data from a financial market, I don't need it. Or if I use a video game example, I just let the video game give me the frames, and I use that to find an optimal policy.
So you need an oracle that provides the path generation somehow.
Yeah, you need an oracle.
Right. Okay. That part I missed today.
So yeah, I just wanted to check here. So this was 500,000 path. To give you a feeling of how long that takes. Probably you can do it a little bit faster because my coding skills are not the best, but it takes significantly longer than dynamic programming.
So
what else?
Can I ask one more thing?
Yeah, sure.
In dynamic programming, also you need to compute these values starting from this. I mean, the conditional expectations starting from different states. So in this way, also, if you're thinking of a game or something like that, you start from the beginning. You see the whole path. And then that's your basic information. You're not going to be able to control and say, okay, I want to start in frame number 42 from the position, blah, 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 because that is not access to you.
Exactly. Unless you have a lot of control over the...
Exactly, but normally you don't have that control, right? So the second algorithm is available, but dynamic program will not be an option.
Exactly.
Right?
Yeah. That's
why I just want to see, the limitation, because I mean, if it is possible to use, then from cursor dimensionality perspective, they are the same, right?
Yes, but in the implementation, you need a way to generate data in an efficient manner, let's say. If you, in the video game example, if you have to run the entire game, so to say, to get one path, which is inefficient. But there are situations where you can actually generate from a given state further. And there are a couple,
then you get closer to approximate dynamic programming because you could eventually not compute the conditional expectations exactly, but use sampling there, right?
Yeah, pretty much.
Sorry for that.
No, great questions. Yeah, and now I've given you a lot of downsides on Q-learning, but of course the important thing is we don't need the exact dynamics. Once we have an oracle, that's the upside. Maybe hinting at what is happening tomorrow, we need to ask ourselves, where do we get all that data from? If we can simulate them, nice, okay. In our setting here that I showed you, this is okay. It's a binomial model. I just simulate, but I don't need to do that if I know what the model is, and then I do dynamic programming. So if I really want to use that in a financial market, I need market data, and the question is, how do I get my 1 billion path? Nowhere. So that's of course an issue. In other situations, this is nicer. You can of course simulate a game of Go. From a given state. That's no problem at all. Up to a certain degree. Another thing which I find is interesting is, so for Q-learning, we want to use it when we don't know the dynamics. If we don't know the dynamics and then the algorithm spits out a policy, how can we check if that's any good? Because we don't have dynamics, we cannot judge. We cannot compute the value function exactly. Maybe we've chosen the wrong learning rate and it throws out something terrible. So what do you do?
To test with perturbations at least, right? I mean, it's not so easy.
Exactly, that's not so easy. So what you do, especially in this financial context, you do benchmarks. Let's say you work for a hedge fund. Still a terrible example, I know. You work for a hedge fund and you've created a reinforcement learning algorithm, model free. You just throw the data at it and it gave you a nice policy. And now you want to convince your boss, use that. Invest $10 million using my strategy. What do you have to do before it will really be implemented? You have to show that it's better than whatever is the current strategy that they're using. And definitely much more tests, because you don't want to bet your $10 million on a black box, right? So this is a very interesting question, I think, to ask yourself. If you really don't know the dynamics, how do you judge if what you're doing is good? You need some kind of benchmark, and that depends on the situation. Okay, let's see. Yeah, that's it. Thank you. One word, tomorrow we will talk a little bit about extensions when we do function approximation, and probably also a second approach, which is not based on this iteration of value functions, Q functions. Thank you.
All right. Thank you very much, Christoph, for this really very engaging and nice presentation. And by the way, I was just writing with Blanca, who was very happy to hear that you kind of advertise her talk, because her talk will exactly be about scenario generation, which is very well linked to the problem that Christoph just mentioned at the end. Are there any questions?
Okay.
I was almost impressed.
Obviously,
Thank you very much. What is the effect of discount factor on future rewards? What happens if it exceeds 1?
If it exceeds 1.
1, yeah.
So if it exceeds 1, you probably want a finite horizon problem, otherwise it diverges. Right?
I mean, the action values diverge.
The value function will diverge, right? Because you're summing up something which becomes larger and larger. So it should be a finite horizon problem. And then this just means that you value late rewards more than early rewards. Yeah, so coming from a math finance background, to me, the discount factor is just something which describes an agent's preferences. Yeah, so the smaller the discount factor, the more you value early rewards over late rewards. And the tipping point is at 1. If you make beta smaller, you want your rewards right away. You don't care about anything that happens later. If it becomes large, you don't care about rewards right now. You just wait all the way until the end and interpolate somehow between it.
Thank you.
Other questions?
There might be in chat.
Yes.
Oh, yeah, that's Blanca saying that I'm just advertising her talk, basically. Yeah, so that will be that really is more or less the purpose. Yeah, financial. Yes. You're welcome. So maybe let me draw the conclusion that I wanted to do tomorrow. So in my opinion, reinforcement learning in finance is not a good idea. Because of that problem, we don't have enough data available. And if we need more data, we need Blanca. She will tell us tomorrow how we can do that under minimal assumptions. But still you make assumptions. And once you make assumptions, you should try to incorporate them into your optimization procedure. The more structure you have available, the more easy it is for you to tell if what comes out is good. So be careful. Don't just throw your real life data at it, because it's probably not enough on the one hand, hard to judge. But hybrid models somewhere in between this raw dynamic programming and this raw data-driven approach, I think this is the right way to go.
All right.
There's a lot of text in Blanca.
Yeah. But still, let's thank Christoph again, and let's head for lunch. So I think we'll meet again at 3 o'clock in this room.